Okay, we're back talking about function notation and vocabulary, and I wanted to talk about evaluating functions in particular. We evaluated a function in our introductory video. Here are three more functions that I just want to evaluate, maybe one or two values for, and then I'm going to talk about the domain and the range associated with these functions. So here are three different functions, all expressed in terms of different variables. This is a function of x. X is the input. The function is the output, which you could call y if you like. For the next one, we have g of t. T is the input, the independent variable. G of t, this function, is the output. And you could call that just g or just y. I mean, you could call that anything you want. Down here, we've got h of n. And notice here that I don't always have to use small letters. I can use capital letters. It doesn't really matter. And oftentimes, when we start getting into functions in a heavier way, it's nice to define the function letter with something that means something to us. Okay. Down here, we have capital H of n. N is the input variable. H is the function. H of n is the function and the output. So let me just take a couple values for each of these. Let's see. Can I stick anything I want here into the x? I think so, and let's just put in, how about 2? We'll start with that. F of 2. My input variable is 2, so I put 2 in wherever I see an x. And let's see how that comes out. 2 cubed is 8, so this is 2 times 8. 2 minus 4 is negative 2. Minus 2 is 16. Minus 2 is 14. Okay. So for the input of 2, I get an output of 14. That actually is an ordered pair. Okay, so no, this input is related to that output in specific. I can call that ordered pair if I want. 2, comma 14. And you might recognize that from your typical XY point on a graph. And so we'll talk about that here in a little bit. Okay, let's put in another value for f. How about a negative value? Negative 1, that's an easy one. This gives me 2 times negative 1 cubed minus 1, or plus negative 1. That's where I get the minus 1. Minus 4 gives me 2 times negative 1, since negative 1 cubed is negative 1. Negative 1 minus 4 is negative 5. This gives me negative 2 minus 5. In the end, negative 7. So there's an ordered pair here. Negative 1, negative 7. Okay, let me move on to g and talk about a few values there. And let's plug in g of 5. Okay, that's really easy. 1 over 5 is the result, so we have an ordered pair there. 5, 1 over 5. And notice that we always put the independent variable first in my ordered pair, the evaluation of the function second. That's typical. Okay. What about this one, g of 0? That would give me 1 over 0. Uh-oh. Anything divided by 0 is undefined. This one actually doesn't produce an ordered pair. It doesn't work. It's not allowed for the function. So that's kind of an interesting concept. There may be inputs that are just not allowed for the function to produce an output. In this case, we see one right there. Okay, keep that in mind. Let me go on to, in the back of your mind, let me go on to h of n. Suppose we had h of 4, okay, square root of 4. Remember, when we evaluate a square root, we only do the principal root, which is the positive value here, 2. Okay, so we've got an ordered pair there, 4, 2. How about h of 5, square root of 5? Well, that's an irrational number. It comes out to an approximate value. How about if I just leave it as 5 root 5? The input was 5, the output was root 5. Well, consider a negative number. How about negative 4? This gives me the square root of negative 4. Now, this is kind of interesting because whether or not negative 4 is allowed depends on the type of numbers we're allowed to get out. So if we're only allowed reals, then we're going to say this is not allowed. Okay, not a real number. not real. If your output has to be a real number, then -4 is not allowed as an input here. However, if your output is allowed to be a complex number, then there is something. We can say, okay, it's not real, but it is 2i. So the output of this is 2i for an input of -4. So once again, it just matters whether or not your outputs are allowed to be complex. So we see some interesting things. We see that sometimes the inputs are restricted, sometimes the outputs are restricted, and those restrictions or definition of what's allowed in and what's allowed out, those are called the domain and the range. So the domain, in particular, is the set of all allowed inputs. And it really just depends on your system whether or not it qualifies as allowed. It's domain. The range is defined as the set of all allowed outputs. So once again, the allowed part of it is what you need to consider. Are you allowing complex numbers or only real numbers or only rational numbers or whatever set you want to talk about? And once again, just to relate this to our inputs and outputs diagram that I made on the first one, okay, here's our inputs. And the set of all allowed inputs is the domain. Let's just say that here are the allowed inputs. x1, x2, etc. The allowed inputs are the domain, or constitute the domain. Okay, and we're going to go from that to an output. Remember, for every one input, there is exactly one output. That output can be the same or different. y1, y2, and I'll just go ... here, and let's put another little weird squiggly set there. Here are outputs, and in my squiggly little set there is the range, which is, here, let me write it the same way I did there, allowed outputs. Allowed outputs equals the range. Sometimes the domain can be defined ahead of time. If the domain is defined and the function is defined, then necessarily the range will be defined by the domain and the function. Sometimes the range can be defined, and maybe that'll restrict your domain. Sometimes all you're given is the function, and you have to determine the domain and the range based on a real number set or complex number set, something like that. So let me go ahead and continue on to other videos, and we will explore domain and range in more specificity with other examples.